Okay, shall we start? I think it's okay. Good. So I welcome you to the second talk of the 11th series in honor of Professor Aryeh Dvoretzky. Aryeh Dvoretzky, Israel Prize Laureate, was a prominent mathematician specializing in functional analysis and probability with classical theorems concerning normed spaces and distributions. Among his positions and roles, he was founder of the Israeli Institute of Advanced Studies and of the Israeli Academy of Science. He was president of Weizmann Institute, chief scientist of the Ministry of Security, member of the Atomic Energy Committee, and won many prizes and honors. I should say that he also wrote in the early 50s, the best probability one textbook to date, in my opinion. Today we'll be hearing Professor Michael Eisenman, professor of mathematics and physics at Princeton University, among the cornerstones of today's mathematical physics, with contributions to almost all of its aspects, including quantum field theory, classical and quantum mechanics, percolation theory, spectral theory of random operators, and many more. He's been awarded many awards and honors, among them the Norbert Wiener Prize, the Breuer Medal of the Dutch Mathematical Society, and the Henry Poincaré Prize. For many years, Professor Eisenman has also been a banner bearer for the philosophy that deep mathematics must also be comprehensible. And hence, I'm looking forward to hear his second talk today, Entropy of Quantum Entanglement in Pure States of Rapid Decorrelation.
Thank you very much. It's a deep pleasure for me. It's always I'm emotional whenever I visit the university, of which I'm an alumnus. And also, it's a great honor for me to give the Dvoretzky lectures. At the first lecture I gave, I mentioned the intellectual debt which I owe Aryeh Dvoretzky's results on the intersection of Brownian motion paths in my work done some 50 years ago of some relevance to the project of constructive field theory. It's also a very special pleasure for a mathematical physicist to talk at a math department which calls itself the Einstein Institute. I think, and in fact, coming from the parking, I crossed paths with Einstein standing up in the lawn. And I'm delighted because actually the subject of today's talk, which is quantum entanglement, was really started by the work of Einstein, Podolsky, and Rosen. So it's all kind of coming back, returning to roots of various circles which intersect today for me. So thank you. Now, after the first lecture which I gave 2 days ago, taking the feedback which I received of wise people in the audience, I slightly rearranged the subject of this one. Instead of a survey of the concept of entropy, as it hops from one field to another, meaning different things, but with some resonances in its uses and applications, I decided to focus a bit more on the entropy as a measure of quantum entanglement in pure states of rapid decorrelation. So the talk conceived in 2 parts. In the first, I will talk about the entropy of the restriction of a pure quantum state to a subsystem and see it as a measure, present it as a measure of entanglement between the 2 components of the system. If these concepts are foreign to some, they would be explained here. After explaining the basic ideas, I would turn to the more technical part, which focuses on conditions under which the entanglement between a domain and its complement is of the order of just the boundary of the 2. Again, I will try to explain that and mention some results. I would appreciate being interrupted and with questions and comments, especially as this subject is not everybody's cup of tea. So let's get going. A template for physics models, classical or quantum, is where you have some configuration space of the physical system. There's a notion of observables, quantities whose values represent physical attributes, quantities you would like to measure, time evolution, and the notion of states. In quantum systems, I would skip the definition how this works in the classical one. In quantum systems, configuration space is represented by vectors in the Hilbert space associated with the model, with the system, sorry. Observables are represented by self-adjoint operators. Time evolution is given by unitary flow. And states, well, states are generally expectation value functional. So its state associates is characterized by the mapping which it associates value to any observable. And as mappings, they are non-negative and normalized and linear. So in quantum physics, say, at least of system of finite dimensional Hilbert space, states are represented by density operators, which are given by rho positive, whose trace is 1. And the expectation value works as follows. For each self-adjoint operator, the expectation value in the state rho is the trace of a rho. It's useful for many of us, I think, to retain the quantum classical analogy. In classical models, observables are functions on a phase space. Expectation value functional is given by an integral with respect to a probability measure on the phase space. So that there are great similarities. It's very useful to be open to appreciate the similarities, but also look out for places where the analogy breaks down. In fact, some of the excitement is there. And that would be the case with the entanglement. So the most elementary quantum system is a qubit. Say, let me remove the arrow. Yes, just a second. Yeah.
The wave function of quantum mechanics, right? State or the configuration space?
The wave function is the analog of what in classical systems is represented by configuration. Classically, the most information you can provide about the system is to say what are the positions and momenta, say for a classical system of particles. In quantum mechanics, the most we can say is to prescribe a wave function. However, there are states which are not pure, and I'll be talking about this difference. So, but the kind of rudimentary representation of what configurations mean would be vectors in a Hilbert space. States classically are not points in the Hilbert space, they are measures on the classical phase space. Quantum mechanically, this would be density operators, rho, with these properties. But yes, in case of pure state, that this operator rho would be a rank 1 projection on that vector. So the simplest non-vacuous quantum system is a qubit. It's a quantum binary variable. It's the analog of a binary system classically. So the Hilbert space is two-dimensional. It's a span of two vectors. These vectors sometimes would be represented as this the column 1001, or else you may use your favorite symbol for them. For example, this would be the up state, and that's the down state. Now, in this basis, regardless of the basis, observables of a qubit are self-adjoint operators, are all linear combinations of four matrices. One is the identity, and the other are these three Pauli matrices. These matrices satisfy the following property, have the following property. The square of each one is 1, so the spectrum is plus or minus 1. However, they have no simultaneous eigenvalues, since the commutation relations preclude that. Essentially, the commutator of sigma x with sigma y is a multiple of sigma z. And this relation, these are essentially the angular momentum type commutation relations. So that's a basic qubit. Then, to see entanglement in the simplest form, one should look at a system of two qubits. The Hilbert space for that is a tensor product. The Hilbert space of a single qubit is C2. For two qubits, you have a tensor product of C2 with itself. An example of an entangled state is the Bell state, which is written here. This is a pure state of the type that was alluded to. The density operator in Dirac's notation is represented this way. I hope that this notation does not cause discomfort. If it does, let me know, and I'll explain that a bit. Explain. Okay. Sorry? Say it again?
It's uncurable.
Uncurable gap. We owe this to Dirac, but I think it's very, very beautiful and very useful. Yes?
What does the two arrows say in the same brackets?
Okay, so I will explain that. So in Dirac's notation, Dirac noticed that there is a certain notation which is very handy, and it permits to simplify various algebraic relations that would appear. So if H is the Hilbert space, its elements are vectors In Dirac's notation, this would be denoted by this symbol. Now, Hilbert space is a special case of a Banach space. That's something which everybody here is comfortable with. Banach space has a dual space, which is space of linear functionals on the Hilbert space. Hilbert spaces are associated, have the special property that they are in one-to-one correspondence. There is one-to-one correspondence between the state and its dual. The correspondence is given by the scalar form. But if you for a moment ignore that, elements of the dual space would be denoted in this fashion. So vectors in the space are this way, presented this way, dual vectors that way. What you do with vector and a dual vector is let this act on that to produce a number. That number is represented by the bra ket. And then, so that's equal to the action of this element of the dual space on that vector of the original space. A nice feature of that is that if you want to, one way to present a projection would be to reverse the order and write, for example, consider phi psi. Now, what's this? That's an operator in the Hilbert space, because when you apply it to a vector alpha, what it produces, I mean, this notation is, these relations are associative. So if you want to know what does this amount to, well, it's the same. This produces a multiple of this vector phi with a coefficient which is the scalar, which is the value of psi on alpha. So if your young sibling would walk in and would be surprised that mathematicians make big issue out of what we all know is through associativity of multiplication, except that that's lifted to this notation. Likewise, if you want to take an operator acting on a vector phi, it's a new vector, and you want to know the value of the linear functional psi on that, you would write it this way, except that then you can read it any way you please. You can put the bracket this way or that way. So this works very nicely. But the one important thing which would appear repeatedly is that whenever you see this combination, that's an operator. Vector alpha is indicated here. Okay? Okay.
Please explain.
Oh, the up and down. The arrows. So the Hilbert space for a qubit is two-dimensional. So it's a span of two vectors. The two vectors sometimes are denoted, they will be denoted in different ways. One of them is to pick, let me go one step back. I described here the Pauli matrices. Take one of them. The canonical choice is sigma z, but it could be any other equivalent. Any other choice would also work. Take sigma z and look at its two eigenvectors. Since sigma z is written as a diagonal matrix, the two vectors listed here form the eigenvalues, with eigenvalue +1 for this and -1 for that. And we denote, sometimes we denote it like that, but for many purposes it's simpler to flatten the notation, and this is just referred to as the up and down vector. That's the meaning of this notation. And when you have a composite system, a system of two qubit, the Hilbert space is a tensor product of two Hilbert spaces. A vector in that, one way to write it is to say V tensor U. That's not every vector is of this form, but you have a basis of vectors of this form. Sometimes that would be also denoted just by V comma U. But these are rather special vectors which are product of that type. The general vector is a linear combination of such. So I would be kind of flexible with the notation, but appreciate interruptions.
In the first slide, you said that if I understood correctly, the first row and the other one are analogous. So this means that states would be.
I did not hear what.
But states would be density operators, but aren't states just elements of the configuration space rather than operators on it?
Sorry, they are what?
States are just elements of the configuration space rather than operators on it, right?
No, classically, okay, the terminology state is a bit confusing. let me take a step back to the roots of the confusion. Classically, when you ask what is the state of the system, classical, we used to think of this as state of the system is given by listing the positions and momenta, classically. But then, to make space for, as a kudo to the quantum notions, to put the two on more comparable basis, some of us like to refer to states of a classical system not as the microscopically defined state, but as a probability measure on the space of configurations. After all, if I ask what the state of the gas in this room, listing the 10 to the 28 or what molecules, positions, momenta for all the coordinates, that's hopeless. So we describe it actually by presenting the profile of the density. So states classically I distinguish between configurations and states. What characterizes the state is the expectation values which it associates with observables. Classically, observables are functions. Quantum mechanically, these are operators. So a quantum state is described by the analog of probability distribution in phase space. That analog is a self-adjoint operator, which is non-negative, and trace 1. The expectation value is the trace of A rho. If you replace trace by an integral, rho by density function, that formula would also hold classically. And it actually guides the intuition towards, it allows you various useful insights. Okay, so rho is now associated with a vector in the Hilbert space. There is always, if you have a, that's referred to as a pure state in the Hilbert space, it's the analog of a delta function, classically. The rho which goes with that would be the projection onto it. And using this convention, projection is presentable in this manner, because when you apply it to any other vector phi, you produce a multiple of psi with weight which is the scalar product of the two. That's a beautiful demonstration of the utility of this notation of Dirac. So the state associated with that is this. That's sometimes referred to as a state vector. As I said, I view this as an analog of configuration classically, but analogy only goes that far. Okay, so now let's talk about a system of two qubits. In that case, as I said, this is not the generic state, but that's a state which is a tensor product of qubit first up, qubit A up, qubit B up, with qubit A down, qubit B down. That's referred to as a Bell state, and I would indicate what role did it play in the discussions of quantum physics. Now, associated with this vector is a pure state of this form, and which is just this ket-bra combination. And as I said, this pure state is a projection. The square of it is rho square is rho. Now, to the extent that a state is a linear functional, when you have a composite system, you may ask, well, what is its restriction to a subsystem? For that, what you care about is the expectation value of observables which act only on one of the components. So that would be another state vector acting in the Hilbert space of the first component. This can be thought of in two equivalent ways. One is it's the density operator which returns expectation values of observables which act only on component A, or else you can also think of this as the partial trace of rho, for those who are comfortable with those notions. An interesting thing here is that although this was a pure state in the sense that rho square is equal to 1, its eigenvalues are 1 or 0, its restriction to a subsystem A is no longer pure, it's this mixed states. It's a linear, it's a convex combination of two pure states. So the reduction actually increases. Now the algebra of that is rather elementary, but the meaning is worth, there's something striking about that. Because classically, if a state of a composite system is pure, the whole thing is described by some delta function in a relevant configuration space, then each of the subsystems in a pure state. Quantum mechanically, we have here a system where the state, the combined system is in a pure state described by a single vector, but its subsystems are not. Last time I talked about the entropy of states. I noticed I should have mentioned it. With each state, both classically and quantum mechanically, we associate an entropy. I intended to speak today about the significance and the origins of it, but that will have to be postponed to another occasion. But the bottom line, the formula for the von Neumann entropy is minus the trace of rho log rho. And those who work with entropies of probability distributions would immediately notice the analogy of that with integral of the density rho of x, well, rho of omega, where omega denotes point, say, on the phase space, times log of rho omega mu naught d omega, where this is an a priori measure, normalized perhaps with a minus sign. So that's the analog of this. Von Neumann proposed to focus on that as the quantum mechanical entropy. The value of this, since rho is a self-adjoint operator, it has a spectrum, and you can compute this trace by using the set of eigenvalues of rho, and you find that this is equal to minus sum of pj log pj, where pj is form the spectrum of rho. You have such a formula for probabilities over discrete spaces, where this trace 1 means that sum of pj is equal to 1. So for a pure state, S rho equals 0 because p log p vanishes when p is equal to either 0 or 1. So entropy 0 means that rho is a pure state. Pure state meaning that it's essentially of this form for some vector psi. And one of the properties of classical entropy is that the entropy of a system which is composed of two subsystems is actually, the two is greater or equal than the entropy of each of these subsystems. To the extent that entropy represents the amount of information which we would obtain by measuring the system, that's one way to read this classical formula. Classically, this is very intuitive and easy to prove. Namely, somehow there is more information to be learned if you measure both A and B than what the information contained or available through the measurement of A alone. So that's kind of trivial. The proof is elementary. This does not go into quantum physics, and that's a counterexample. Because here we have a system where the combines, the entropy of the system adds up to 0, it's a pure state. The subsystem does not. Well, quantum measurement does something to the system. Actually, this is not a passive operation. Quantum measurements affects the system, and that's somehow at the roots of that. I would say more about that. What happened in going from this to that? I just wanted to... Sorry, do I have the inequality wrong?
Right, the left-hand side is 0, the other one is twice.
Right, so that's classically. So classically, this works, quantum mechanically it does not. What I'm saying is that quantum mechanically this is 0 and that's positive. So the classical relation is violated in quantum physics. And it's violated because the act of measurement does something to the state. It's not there's no passive, almost no passive measurement. Actually, you should feel free to challenge whatever I say. And the Nobel Prizes were awarded for people who figured out how to reverse notions which people just repeat. There is something like rather passive measurements, partial measurement. There are such things. And had you discovered this first, you would by now have a Nobel Prize. Sorry?
What is formally corresponds to the measurements?
Okay, I'm glad you asked because I have this on the next transparency and I was hesitating whether to show it or not. What's a measurement? What is repeated often in classes of quantum mechanics is that whenever you measure something, the wave function collapses. And that is a cause of a lot of consternation and discussions and soul searching, because after all, everything you do is guided by a unitary evolution. How can a unitary evolution take a pure state onto something which is not? How can it change the spectrum of that? Well, here is how it goes. The way you, for example, if you take a system like the Bell state, in a state like this one, of two components, and say you want to measure the value of the sigma z observable for the first component. What you would do is take this system and pass it in front of a machine, kind of briefly let it fly through perhaps, and the machine would have some arrow or some other way to communicate what was observed. So there's interaction between the system, which depends on the state of that observable we are measuring, after which the machine kind of arrow would point, would give you the information was sigma z up or down. Now it's a unitary evolution. So one way to model it is that when you pass the system through the machine, there is a unitary, not a bad representation of the essence of such a unitary mapping. You are multiplying it by unitary and its complement, so its Hermitian conjugate to the left. That's the state after that. And if there was an interaction between the system but only the A component, omega represents an omega which represents the machine which was involved. You may be part of it or not. That's not important. Consciousness does not play a role, I think, in that. But the fact that the particle interacts with a system of many degrees of freedom, the result would be a state which can be written in this form. And when you spell what it means, there are 4 terms. The phases cancel on this combination, but on the cross terms, you get multiplication by e to the I delta theta, and here e to the minus I delta theta, where delta theta is the difference in the phase associated, which picks up the state up versus the state down, and it depends on the machinery. If you run it once again, that phase is practically irreproducible. That's the big assumption. There's a difference between letting this double qubit system interact with another qubit or 2 or 3 versus a machinery which records something on big scale. So if there are many degrees of freedom and this is practically irreproducible, then for practical purpose of taking the expectation value functionals, the phase which you pick on each run through the machine averages to 0. The unitary phase factor averages to 0. So that kind of explains why it's a wise thing to say, you know what, don't keep those factors where this e to the I theta would change uncontrollably between one measurement and another, just drop them. And then you find that, to your surprise perhaps initially, that the state which was in a pure state, so the pure state evolves into a superposition. Spectrum was changed. Now, there is a lot of agony over that, but I think that, to my taste, that's a good enough explanation. I cannot resist the temptation to tell a story here. When I came to Princeton, Eugene Wigner was still around and was occasionally visible. And what I heard about the seminar were a result by Klaus Hepp, which proves this in the infinite for large systems in the infinite volume limit. Arthur Whiteman presented it, and Eugene Wigner was in the audience. And in his manner, he interrupted the presentation saying, "Professor Whiteman, excuse me, you are a great man, but you are not infinite." Meaning, mathematical theorem is that this converges to that in the infinite volume limit, when the observing apparatus is infinitely many degrees of freedom. So I'm sure you have seen weak limits and similar puzzles also in the classical setup. So in any case, I think that this collapse of the wave packet, which is this change in the spectrum of the state, to my taste is sufficiently explained by this procedure. But as I said, there are weak measurements which came up on the scene later, and there things get somewhat more delicate, and that's a fascinating subject of itself. Now, as it turns out, entangled states are a resource. Sorry, I did not say what is an entanglement. Despite the first inequality, the first inequality does not go through, so let me write it. The inequality was that S of rho A B, classically this has more information than A alone or B alone. Quantum mechanically this is not true. However, various other properties of entropy do go through. So for example, the entropy of rho A B is less or equal than entropy of A plus entropy of B. Again, the classical explanation is elementary. If you learn, because another way to state it is that the entropy of rho A, B minus just rho, say, B, that's referred to as the conditional entropy of A condition V, because it essentially expresses how much, I'm talking about the classical case. S of A. Classically, this can be interpreted as the amount of information you would gain measuring A if you already know B. Quantum mechanically, this already know part of the story, of the statement is complicated. And this can be restated by saying that what you will learn about A knowing B is less or equal than what you have learned had you started from the state of ignorance. So that's another way to restate this inequality. That actually is true quantum mechanically, and I talked about it last time. There is also strong subadditivity, which I talked about last time, but it will not play a role today. So some features of the entropy go through. The one which drastically does not is that. But what I wanted to note is that having entangled states is not just nuisance, it's now appreciated as a resource. As it turns out, there's an algorithm, a procedure for the quantum analog of teleportation. But let me just say this, but you may have seen this movie, what was it? Star Trek. In Star Trek, there is a spaceship which surrounds a planet, and when Captain Kirk wants to go down to a planet, he uses teleportation. You walk into a chamber, your body is scanned, and the information radiated, and it's reproduced at the designated place. Invoking that, a procedure was developed for a teleportation of a quantum state. The proposal was in this paper by Charlie Bennett, 1993, et al. I sit here, Asher Perez is there, and Repos, Yosa, and Brassard. What else? Teleporting an unknown quantum state via dual classical and EPR channels. What it means is that you may ask yourself, if I have here a quantum state, I cannot measure it and pass the information by phone because the act of measurement ruins it. So how can I pass this state without, reproduce it elsewhere without just taking the 2 qubits? Well, there is a procedure which works essentially as follows. You initially equip the 2 endpoints, the 2 labs, with qubits which are entangled. And then there's a measurement you can do on your system, telephone or pass by any classical algorithm, the result of it to the other lab, and they would do something to their qubit which would guarantee that the state of that qubit was the one which you destroyed by your measurement. You can do that. That can be done. Also, correspondingly with what can and cannot be done with Captain Kirk, you cannot duplicate a quantum system. There's no algorithm for that. But you can teleport a quantum system. And for this teleportation, having entangled pairs is essential. So it's really a resource. It's not just nuisance. Such a teleportation reportedly was successfully carried out by 2 research groups of Popescu and Zeilinger, who received the Nobel Prize for his work on quantum systems, in particular this one, among which was this one. So far I talked about qubits. Let me go to more general composite systems. And now there is a remarkable, some of what I'm saying are remarkable aspects of rather simple algebra. Just have to keep an open eye to recognize it. So there's a remarkable statement which is referred to as the Schmidt decomposition, which is as follows. In a product space of, say, tensor product of HA with HB, any vector is presentable in the form listed here. Namely, for any vector psi in the product space, there exists a choice of bases AJ and BJ for the 2 components, in which the vector psi looks like that, essentially like the state which I described before. Instead of just sum of 2 perfectly correlated states, it may be sum of a finite number of such vectors, but essentially it's a finite number of terms of this type. The number is referred to as the Schmidt rank of this vector. And of course, since these are orthonormal bases, it does not exceed the lower of the dimensions of the two. Now, not only that, and these pj's are positive numbers, square roots of positive numbers which add up to 1. Now, what this representation implies is the striking statement that for a pure state, if psi was a pure state, its partial trace, when you integrate out the b variable and restrict just to a, is of this form. Sum of pj and then projections, aj, as we talked about, aj projections. The partial trace on the b component is of the same form with identical spectrum. And that's remarkable because the two subsystems may be very different. The Schmidt rank would be dominated by the dimension of the smallest of the two. Okay, so every vector in the tensor product is presentable this way. The restrictions of the states are of identical distribution. And now it's natural to regard the entropies are in particular equal because they have the same spectrum. It's natural to regard the entropy of this restriction as a degree of AB entanglement. After all, this transition from a pure state to this occurred by breaking the entanglements which existed in the state. And as I said, entanglement is so you do not just count what's the dimension of it, but you take into account the contribution of that into the state. That's the link between entropy and entanglement. It's one of the measures of entanglement. I just wanted to say that in the case of a pure state, this up to a factor 2 coincides with what's referred to as a mutual information. The mutual information between two components quite generally can be presented as the deficiency, the inequality, the difference between the right and left-hand side in this subadditivity. So it's the sum of the entropies minus that, or if you wish, the difference between the conditional entropy and the unconditioned entropy. That's a general notion of mutual information between A and B. In case the two are in a pure state, this is 0, and that's just twice the entanglement entropy. That's the first part of the presentation which I wanted to make. They are not going to be of equal length, I assure you. The results which I wanted to present, which requires somehow the more nuts and bolts analysis, have to do with the extension of these ideas to large systems. Systems of the type that may be of interest in either statistical mechanics or in computational algorithms involving many degrees of freedom. So the general picture here would be that you have some big assortment of qubit or qubits, kind of quantum degrees of freedom associated with sides of a graph. You have a state psi on all of that, and again, you may be interested in the degree of entanglement, where the entanglement now would be between the degrees of freedom within some subset A, in which you have many of those, and its complements. The whole thing would be denoted by W. So the notation is, as indicated here, the Hilbert space is now a tensor product over U, which are points in this big region of Hilbert space HU. Rho A, as before, is obtained by tracing out the other degrees of freedom. And entanglement entropy would be, as before, if you started from a pure state, it would be trace of minus trace rho A log rho A. More explicitly, what's written here. Now, a significant aspect of this condition is that when you look at the spectrum of rho, the trace is equal to 1. So there is somewhere the maximal one, which is less or equal than 1. Next one, these eigenvalues cannot accumulate except at 0 because they add up to 1. The number is actually potentially very large because the dimension of the space. Trace of rho log rho is evaluating a sum which essentially of a function which looks like that. So it's rho log rho, function of this. And what you are adding are the values of this function. And what makes it into somewhat challenging analysis is that the condition that trace is equal to 1 means that these low eigenvalues are summable. But when you evaluate the rho log rho, there is room for unduly large contribution from the low eigenvalues. We do not worry about the largest eigenvalue, the next one, the third one, but the small eigenvalues, that's where the information to some extent lies for that. And that makes the analysis a bit tricky. Now, general bounds on this, as I said, in case of pure state, this is twice the entropy of entanglement. General bounds go as follows. There is so-called Page's law, Page, the name of the person, which is that if you choose rho generically with a measure which is invariant under unitary rotations in the big space, kind of random rho in this sense, uniformly random, the entropy would be of the order of the volume of A. However, if the state is of the form e to the minus beta h, kind of thermal state applied to a seed vector, or just thermal state, corresponding to a Hamiltonian, term I have to explain, but an interaction of finite range, I hope that makes some sense. In such situation, the entropy would be bounded by beta times the size of the boundary. There is a general expectation that when beta tends to infinity, you are looking at the ground state of a system, of a very large system with macroscopic number of degrees of freedom, so large number of degrees of freedom. It's expected that for non-critical ground states of such a Hamiltonian, the entropy would be of the order of volume. Boundary, or at least boundary times the logarithmic correction. That's the question on which I wanted to report in the second part of the talk, but I may not get to say much beyond just quickly flash some highlights of that point. And I prepared the transparency. I don't want to skip over that, which is a commentary before we turn the page on part one. So, although I presented the Bell state before, the recognition of quantum entanglement emerged from the seminal work of Einstein, Podolsky, and Rosen in 1935. Their initial motivation was to point out that there are some puzzling aspects to the quantum theory. The question was whether it provides a faithful, complete description of the physical system. They brought some objections, and there was a back and forth exchange with Bohr and other founding figures of quantum physics. It was a few years later that David Bowman, our Yakir Aharonov, sharpened the argument, directing attention, distilling the EPR argument, paying attention to what they call the EPR state, which is what's written here. There's much which I could say about this state, but it's essentially equivalent. It's unitarily equivalent to the Bell state, which appeared here. Their purpose was to really address the issues of, basically, if you want to think about, what they pointed out is you have problem, Einstein, Rosen, Podolsky kind of agonized, not agonized, in fact, to my taste, they presented to the world deep observations about the implications of the theory, especially if you try to stick with the notion of no action at a distance. Whatever you do to A here cannot instantaneously change B there, and yet there is this hidden correlation between them. And there was a discussion of that. John Bell, a bit later, presented this state, which is essentially equivalent to that, but he used this to produce relations between observable probabilities of various events, which should be inconsistent with any attempt to produce simple hidden variable explanation of the difficulty. So the object of that. So during this period, there were kind of deep-wrenching, agonizing discussions of philosophical nature about philosophy of quantum physics. Richard Feynman had the healthy empiricist view, which, I mean, his pronouncement on the subject was, as you might have heard, shut up and calculate. Just don't agonize over that. The theory permits you to calculate various scattering amplitudes, quantum electrodynamics, and so on. Just do that. Don't put aside. I think the generation which came later, from my perspective, reminds me of kids in a toy store. So rather than agonizing beyond the epistemological debates of what the meaning of things, what many physicists, what some leading physicists do quite successfully, physicists and nowadays also computer science, is to ask, gee, that's cool, what can we do with that? And they produce various cool applications of this tantalizing theory. Among those is the teleportation, which I mentioned. So it's like kids in a toy store kind of playing with that. And for them, entanglement is a resource. Now, I have 5 minutes to summarize what I wanted to say about in the second part, which are bounds, area bounds on entropy. So perhaps, okay, let me just quickly read this and then come to the next transparency. Some of the analysis, as you know, in analysis, positivity is a very valuable feature. If you have it, it helps. It allows to simplify analytical results. In fact, sometimes it's really essential. So some of it shows up in this discussion. Quantum states, which can be presented in this fashion as sum over a certain basis, it's so-called computational basis, of pure states weighted with positive weights. In this representation, the states are referred to as stochastic. The term stochastic combines quantum with stochasticity. So there are various models of interest, various systems of interest actually in the natural states of interest are stochastic. And the analysis there is a bit simpler. And what I have to say first can be demonstrated on that. So here is a kind of the key idea of how to approach potentially entanglement bounds. So if what you care about is the state reduced to system in A, surround A by a buffer, and if the system has short decay of short range correlations, if you are lucky, you may find a state psi AB, which is a quantum state of the system in AB, with the property that its restriction to A is close enough, in some sense, to the restriction of the original state of the huge volume. If you found such a system, then perhaps the entropy of the restriction of A would be well approximated by that. And if the approximation is good enough, and that's where the kind of rubber hits the road, the analysis, then you can use the fact that the entropy of entanglement is dominated by the Schmidt rank of that operator, which is at most the dimension of the buffer. Intuitively, if you allow me to kind of oversimplify to a point that I do not quite understand what I'm saying, but intuitively, if you have a say ground state of a Hamiltonian with short-range correlations, you may expect that the state may contain kind of Bell type of entangled states, or slight extension of this, which are short range. When you restrict your attention to a subset A, you lose the coherence of those clusters which go across the boundary. So you may think that intuitively it would be the number of those, so to say, which represents the degree of entanglement. That's kind of the guiding thought. Making sense out of that is very difficult and was not fully accomplished yet. But the purpose of the analysis is to connect with that intuition. So what we do, and what I'm presenting is a joint work with Simone Warzel. The trick is to seek a high fidelity approximation, which is of low complexity. Low complexity means essentially states supported on the buffer of volume much smaller than A. And if the state is stochastic, it can be described by a probability distribution of configurations in A, B, and C. That probability can be written as a product of probability of configuration in B times the conditional probability of C given B, and then conditional probability of A given B and C. A natural candidate for an approximation would be to choose a state which is of very similar probability, except that at this point you drop the dependence on C. Namely, you consider a state which is obtained by integrating of what happens in the buffer, and produce a state in which you let A and C conditionally on B be independent. The question then is, how good an approximation is this state to the original one? And there are various technical points which I would not have the time to go over, but that's where the analysis lies. The bottom line is that in the case of the quantum Ising model and various systems which share properties of that, we actually managed to prove that the quantum Ising models, ground states, exhibit area size entanglement with an extra log for states up to the model's quantum phase transition. The last thing which I want to say before I stop, because the details of that probably I will not be able to communicate now, to represent well now. I want to just alert you to one thing. Had this been, for those who heard about the Ising model, it's a system with short-range interaction. You may be tempted to think that this idea actually should solve the problem quickly because you have the Markov property. For systems with short-range interaction, if this width is larger than the range of the interaction, conditioned on B, A, and C are strictly independent. So why isn't the discussion finished there? The answer is that because of the non-commutativity of the elements of the Hamiltonian, you do not have the Markov property in these quantum systems. You may have some echo of that, some approximate version, but you do not get it. In a way, again, it's something which deserves full explanation, but in a way, the quantum Ising model, whatever that is, the ground state of that can be viewed as the restriction of can be computed in terms of the classical Ising model in one extra dimension. And what we are talking about is something like, it's not fully correct, but has some of the flavor. If you think about a system of D plus one dimensional system, say ZD plus one, then let me draw it in case D equal 1. So I'm taking a cross section in this direction. It's like a discussion of Ising variables along a hypersurface of, say, time 0. And the conditioning which we are doing is we are asking what is the conditional distribution in A conditioned on B. However, A and B are restricted to a time 0 line. So quantum mechanically, you do not have the Markov property because you do not encapsulate the region all around. However, you may expect that with rapid decay of correlations, there may be an approximate independence. And that's what the work focused on. These are some details which I will not have time to explain. I quickly would flash some of the references which are relevant for part 2. In particular, very useful results were contributed by Anshu, Arad, and Gosset. Bjornberg, Grimet, Crawford analyzed the Ising model, but only in one dimension by a different technique, and the result which I presented with here, which go back to that work, actually we are pleased to be able to get all the way up to the critical point. What we did not do, and I do not know yet how to grasp, is how to analyze the ground states of a quantum Ising model in the phase in which there is symmetry breaking. It corresponds to the quantum system which you obtain by looking at the restriction of D plus one dimensional Ising model in its symmetry broken phase. For those who understand that I think there is room for better results there yet. So to summarize, there were 2 parts to the talk. This is just a reproduction of the abstract, and it remains for me only to thank you for your attention. Thank you.
Non-focused question. Classical versus quantum. I mean, what in the mathematics makes the distinction? I mean, also in classical mechanics, you have a measure of the flow, you have the subsystem, interactions. What in the model makes such a difference between quantum and classical?
The non-commutativity of the observables. If K is an operator, e to the beta K is, of course, sorry for saying it, it's sum over n from 0 to infinity. beta to power n over n factorial k to power n. For a probabilist, you can present it differently. You can say, let me subtract from this k, then I have e to the minus beta. This is the Poisson random integer. So the exponential of k, and k should be thought of as an operator, can be presented as the expectation value of k raised to some power n, where n is a random integer. Now, something like this happens if you also, when you take the exponential of beta sum over alpha of some operators k alpha minus identity. The analog of this representation produces the following thing. You are integrating over, so now I will do a picture which explains what's there. Think of the time, there's a beta here which plays the role of time. Think of the original graph on which the system is formulated cross the interval 0 beta. And now consider a Poisson distribution of kind of ranks which represent the interaction terms, alpha. Take a Poisson distribution of ranks on this randomly placed ladder. Each object here represents some interaction term which was activated at some time. The formula says that the exponential of this operator, which is sum of non-commuting terms, can always be represented as a probability distribution of, and then for given omega, you take the time-ordered product of the actions of k alpha t, kj. It's a time-ordered product of that. So the partition function of a quantum system, which is sum over it's a trace of that, is integral over d plus one dimensional activations of such operators, where the way it works is you just think of the time, you run it upward and you act on the initial vector psi with this. So actually you are naturally, you find that there's some correspondence between the two, but the quantum physics is related to operators which are somehow formulated in terms of what happens along a particular time slice of a system where there are interactions before and after that. Now that was for the Gibbs measure. You can also, rather than applying this for the Gibbs state, you may actually engineer some system of quantum gates where you by design consider the effect of carrying out these operators followed by those operators. They may not commute, but you can indicate in which order you act. Classically, when they commute, the order does not matter. You can just collapse everything on one time. The sequence of operations does not matter. Here it makes a lot of difference. So sorry for the long answer, but that's the... Yes?
What is the role of criticality? Are you using a gap condition or...
Yeah, criticality. So since I explained that the ground state, I indicated at least, that the ground state of a quantum system like quantum Ising model can be viewed as some story related to a classical model in 1+ dimension. Notice that this classical model actually undergoes a phase transition. In terms of quantum systems, we are talking about the ground state, but there is a parameter there which, as you vary, as you tune one of the parameters in the Hamiltonian, the quantum state, which is observed along this slice, switches from having rapidly decaying correlations to a state which exhibits long-range order and sensitivity on boundary conditions which are very far. At the critical point, the correlations decay are particularly long-range. Once you pass criticality, there are two phases, each one of them only short-range correlations decaying exponentially. So there is this notion of phase transitions which quantum states, ground states of an extensive system undergo at 0 temperature. That's referred to as quantum phase transitions. They correspond to classical phase transitions in one extra dimensional system. So what's important for the analysis is the rate of decorrelation, and that's where the criticality makes a lot of difference. So thanks for asking this. It gives me a chance to say things which I wanted to.
Okay. So you talked about quantum Ising model. Are there analogs to other models, familiar models like Potts model?
Yes.
There are quantum.
There are, and one thing which I love to see, and there's a joint work which we did with Hugo Dumnil-Copan and Simone Warzel. There is a system which some of you may have seen before. There is a system of random loops that will be in space-time.